Ashutosh Saxena from University Cornell.
So today I'm going to talk about how I look at things when I'm designing some machine learning for robots. For me, the way robots learn is by interaction. And today in different talks, you may have seen robots learning by interacting with the real world. So I will describe how can we design learning algorithms for scenarios where you are not just classifying one thing into another, but a robot is interacting with the real world. And also often robots need to share knowledge with respect to one another. Like they learn at one task, they share it with another robot running somewhere else in the world. So how can we design learning algorithms and representations that can do the same? Let us look at the recent progress in deep learning, not some of the talks that we saw today, but earlier. Most of the tasks that deep learning was solving was taking an input X and outputting a label Y. It has been hugely successful at that. For example, taking pictures, putting a label on it, or doing a little bit more intelligent representation of the image, which is labeling it in different pixels of the image with different categories, and so on and so forth. It was applied to language and so on. Most of them were constrained to the task of X, given X, label Y. One thing recently that we also noticed that by applying a little bit of a structure to deep learning and designing these structures more intelligently, we can encode our intuition about the tasks and make them perform better. For example, just in the last task we saw that training a neural network on one task of playing Pong and slightly changing the task to do something else is quite effective because we are relearning, reusing the learning that was performed on another task. And these are some other examples. For example, if you know the structure of this particular problem, that humans are configured in a certain way because of kinematics, it is much better to encode and design an architecture that takes that into account. And so on and so forth. There have been many works which combine structure with deep learning neural networks to make them perform better. So one thing that I will cover in this talk is try to figure out how we can figure out what is the structure, what is the representation, what is the human intuition we need in order to make it work for robots. So let us first look at the different robot tasks that we do. So this talk will be divided into 3 parts. Interaction, so where I will describe a few different projects I have been working on in which robots are trying to do different things. And these are just some examples. For example, robot manipulation, when robots are trying to work with people to do something. A self-driving car or an assistive car in which a human is driving the car, but there may also be situations where human and automation may kind of intersect with each other. They may try to do different things, or car may do something to avoid human doing something. And also natural language processing and other manipulation tasks that a robot has to do. The fundamental thing that comes out in each of these tasks is that the robots has to interact with humans and the environment and also the internet in order to acquire these skills. And each of these tasks may be so different. One thing which is quite common in all of these tasks is the structure. By structure, I mean is that in order to perform one complete task, for example, this one, a robot should ideally be able to understand the kinematic behavior of the humans, which is how humans are moving, what they are doing, the objects in the environment, and also kinematics that go towards with it. Even further, it is a task in which decision making may be involved over time. So there are many such different components that are involved that the robot should try to or the learning algorithm should try to model well. So therefore, I will spend some time in presenting to you one of our recent works that we are presenting at CVPR, which describes a general framework to model such a space-time interaction for many different tasks. So that would be the second part of the talk, in which how we can take many such of different tasks and create a generic method that can handle them. And thirdly, I will briefly mention one of the projects I've been doing for the last few years, which is Robobrain, where we can take many of these different tasks in different domains and share that learned representation many times using deep learning through a cloud-based service. And most recently, what we were able to demonstrate that a robot, PR2, that was at Cornell University in Ithaca, was able to learn certain things upload it to the brain, which was hosted at Stanford at that time. And it was that knowledge, that those representations were downloaded by a Baxter robot in a different university in Stephanie Telex's lab at Brown to perform some other tasks. So this is one of the first examples which shows that a different robot can share its knowledge across using the cloud representation and perform another task. Anyway, let me go into a little bit more detail and describe to you the first couple of different examples that robots have to do. In my own lab, we have been looking at robot language, intersection of robot language with manipulation, where this robot is trying to do something at the barista machine. A lot of force contact manipulation, where a robot is trying to cut food items. This is an example from Peter Abil's lab, where there's contact manipulation with the ropes going on, a lot of human-robot interaction, and also something that I've been doing recently, which is to treat a house or a home as a robot, which is interacting with people all the time. Let me pick one of the examples, which is a little bit more concrete, and describe what a learning algorithm has to do. So this is just a video from one of the other recent projects that we did in our lab. I don't think you can hear it.
As drivers, we trust ourselves to make the right decisions. But we rarely detect disaster until it's too late. Our sensory technology anticipates your actions before they occur, giving you just enough time to make all the difference.
All right, the point to take home in this video is that many of these physical systems, such as cars and robots, are working with humans all the time, and they have to interpret a lot of data streaming in, including the way a human was behaving. So in this particular example, we collected over 1,000 miles of data from 10 different drivers in a large neighborhood. And this particular problem, the goal was for the car to anticipate when something may go wrong in the future. For example, the driver is driving straight, and by looking at his behavior, people often tilt or look to the right before they actually make the turn on the steering wheel. So if a car could know that the person is about to turn right and there is a biker coming, it could give a more aggressive warning and avoid that accident. In this case, the learning algorithm has to parse different inputs. It has to parse all the logs of the data, which include GPS and all that information, but also information such as the face information of something looking at the car, the driver in the car, and also the outside world. And we have seen many examples in the past, and this was a work from like last year and published this year in ICRA, is that if you design the right architecture of the deep learning algorithm, which I'm not going to go into detail into, but if you take the low-level inputs from different modalities, throw in some layers, and then you combine them in a fusion architecture, and you also connect them in a temporal fashion, you can actually make such predictions. And this kind of architecture often performs much better than other algorithms. At a very high level, this architecture is essentially doing which we have been doing over the last decade or maybe even 30 years, which is treating it like a hidden Markov model or a CRF, where you have time going in this direction and you have observations going in this direction, and by using human intuition, you were able to combine different sensing modalities. The only thing that we did here was to replace each of those observation and transition probabilities with a kind of a neural network. And that allowed us to get very high performance in making this problem work. It turns out many other problems are very similar. Let's look at robot manipulation. Let's assume a robot which has to manipulate like 50 different types of appliances, which include door handles, wash basin sink. Don't ask me why one of the students took this data point. But or coffee machines, for example. And in this case, the problem is also very similar. One has to take these components which we have intuition about, which is that there is some robot kinematics. I don't think we should be actually learning robot kinematics, like that is often known and something that could be actually given to the robot. But combining that kinematics with natural language instructions and the data that you get from sensors, for example, 3D sensor or images, and designing that architecture, in this case, the joint architecture is not too complicated, is the key that allows us to handle many such robot applications. So this was a Robobarista project in which we combined this manually by figuring out how these different modalities connect to each other and how they affect decisions over time. And there are many such examples, right? We had another project called DeepMPC, in which we took an existing known algorithm in robotics called model predictive control. And in that case, we just replaced each of those boxes with the neural network functions, and that allowed the robot to perform very, very nuanced manipulation of food items. It was presented in RSS about 2 years back. I'm just showing these bunch of different examples to give you an idea about how complicated and how hard our robotic tasks are. And each of us work in many, many different domains. Some of us work in language, some of us work in only kinematics and manipulation, some of us only do perception of human tracking and so on and so forth. But the real question that becomes is how can we learn this varied form of data, which is the second part of the talk I'm going to talk about. So I'm going to present here a generic framework to model these space-time interactions. That is what we will start with. And this is just one example of such data where, for perception purposes, if a human is moving around, you know the kinematic structure of the human already. And if there is a method to encode that known intuition into your deep learning architecture, it could become very, very fast to design a really good performing perception algorithms for figuring out what the human is doing. In another example, if you are doing some manipulation with a robot doing something and there are some forces involved, there's known kinematics or model predictive control involved, well, if you know some of those intuitions already, which are actually precisely known because of known physics, we can model those interactions with deep learning, and we will describe that going forward. The generic idea that we will start with is the following. What we will do is this is an illustration. The actual net is much more complicated because you don't have nicely segmented objects out. But the idea is the following. We will take our problem, and it could be many problems, but we will right now focus on activity in the next 10 slides. And we will define what the different things are there in that problem. In this case, it turns out there are objects, there are humans, there is time. So if you're trying to do human activity detection or anticipation or tracking or any such problem, there are usually a couple of entities, which is human, which has the kinematics, there are objects and background, and they are connected to each other in the following way. That's the second row. That's the first step of encoding what you kind of believe in before trying to apply any learning algorithm on top of it. So usually, historically, what people did was took this graph and tried to write a probabilistical model or a conditional random field model to work with this. In this talk, in this work that we are presenting, what we do is we figure out a way to convert this graph into a corresponding structural RNN in order to make that work much better. The main point here is that this approach, this algorithm that we are going to present, must be obviously scalable and flexible, that if you are increasing the number of objects in the room, increasing the number of scenarios, it should scale linearly in the number of these RNNs that you have. Second thing is that it should be generic and principled, which is extremely important because some people are experts in designing deep learning algorithms, and they actually, if you read their papers, it's often a little bit not clear how much human intuition actually went in while designing those actual experiments. So once you talk to the researchers who are actually wrote that deep learning algorithm in question, they're like, oh, I decided to have this 128 and 16 and this layer and that layer. I was like, so why were you doing that? They're like, oh, I tried 10 different things and number 2 worked better, and that's the usual answer. It's getting principled, and this work is attempting to solve that particular problem. The second thing, very interesting property of our approach is that this is also end-to-end trainable, which means that the way you design these wiring between the RNNs actually allows you to have still reasonable training at the end of the day. So we don't have time to go into the full details, but I will present you the high-level steps of how to transfer the problem, transforming your problem into a structural RNN. And the way it works is that you first come up with a factor graph parameterization. Now, that is not actually a probabilistical model. It's just telling you that take a problem and figure out what are the different components that go in there and write it down in the form of a factor graph. And a factor graph, for example, for a human tracking problem would be very simple. Each link would be a node, and two links, which is the different parts of the leg, would be connected by a factor because they affect each other when you are moving your arm. Similarly, if an agent is moving around in the time part would be yet another factor because of basic Markov and time effects. You are here at time t, you can only do certain things at time t plus 1. The second step would be to semantically partition the node. Here, previously, when we were working with conditional random fields, the thing that we did was to manually design many of these features. Here, the only thing that the designer of the system that he has to do is to basically say, these are the different types of nodes and factors we are dealing with, and just label them. For example, time properties are very different from space properties. So one can help the system, the learning algorithm, by labeling them as time and space properties. Then we will model each factor with a RNN, and then we will have an algorithm that will take those RNNs and wire them to form a structural RNN. That's about it. So part number one, let's go into a little bit more detail. We take our graph that we know we created by some human intuition, and each of our robot problems, you can actually come up with such different graphs. I'm taking the human activity detection and anticipation as an example, but this could be applied to many different robot problems because most of them have a form of a spatiotemporal graph. Things happen in time, things happen in space, and so on and so forth. Here in this case, we have edges which represent objects and humans, and this is the time part. So these are the node factors which represent the observation of the object itself, which means that if you are trying to figure out where is the object, the pixels in the image that will tell me what that object is represented by this node factor. The relationship between the two objects is represented by these factors, this factor, and relationship between humans and time is represented by this factor, and so on and so forth. So you come up with this representation. The second thing that you do is just label these different types of factors into categories. Obviously, it would be kind of a bad idea to have the same RNN run for time edges versus different edges because they just behave differently. So all you have to come up with is a set is that, okay, these edges, this color and this color are same. Doesn't matter when they happen in time, as long as an object changes its properties in time to another object, the edges remain the same. You can actually sometimes even use the same type of edge for human to human. In this particular experiment, we just had a different category of these edges. Then you have human object edges, which are different from object edges, and that's about it. So that is semantically partitioning or labeling the different types of factors in the graph. And why do we want to actually share factors? That is very obvious. So you can transfer the information learned from one concept into another, and I will show you some examples of how that works. And here's one particular example. Let us say you actually trained a system of this robot using this cup and trying to figure out how a human is using the cup, and then you figured out how a human is using this microwave and putting something inside it. In a third scenario, you may be having a robot using some other object and using it. So if you think about the space that you are addressing by doing this compositioning, it becomes large because you can take any edge and create new compositions, and that helps the learning algorithm see a large number of possibilities rather than seeing them one by one together at a time. Third thing that you do is take your favorite algorithm and put it in. In this case, what we did was we used RNNs, and we had different kinds of factors, which is the vertex factors and the different kinds of edge factors, just replace them with the RNNs, with node RNNs and edge RNNs. And there's a lot of flexibility is there in designing these RNNs. You can actually choose which RNNs suits which kinds of different edges. For example, for node RNNs for objects, you may want to use something that can well classify the classification problem of taking the pixels to an object label, which is what a lot of previous deep learning work has been about. For transforming in time, you may want to take a type of neural network that can transition things through some transformations much better. Last thing you do is we have an algorithm that takes this factor graph and converts that into a wired RNN, and it turns out that this structural RNN is a bipartite graph, and it is very, and there's a very nice learning algorithms which we don't have the time to go into, which can train these systems using existing training software. So you just have to give this structure and these modular connections to existing training methods, and the model get trained. I will show you more interesting parts now. Actually, before that, just to take some key takeaways. Different robotics problems can be represented in a very nice structural fashion in space and time, and even decision-making problems could be represented in the form of a factor graph. So that's where we start with. Then we create these each factor with edge and node RNNs, and then finally we replace each of them with wire to create the structural RNN. We applied it to a bunch of problems, starting with a very, very standard problem for modeling human motion. It is there's standard data sets in computer vision community to do this, where you're trying to model how humans move, and it is obvious and has been known over decades in computer graphics and computer vision. Then, well, if you want to model humans, use the kinematics, known kinematics. And some of the recent computer deep learning papers also encode it, but it often comes down in the form of a random human intuition. Okay, I'm going to do this. Don't ask me why I did this. In this case, what we're trying to do is to come up with a principled approach that can take any such graph and convert it into a structural RNN. Second problem we considered came originally from my own lab, and there are the other papers in which you're trying to model human-object interaction, which is of interest to robotics. Third one we tried was maneuver anticipation, which I just showed you the car video about, in which there is a stream of images coming off the driver, a stream of images coming from outside, and some other logging data that robots always get. In the case of car, it is GPS and such information. In the case of car, this problem came out to be very simple graph like this. There is an outside context, there is an inside context, there is a driver, and the driver is the one which is doing things in time. So yellow edge is the one which is doing things in time. So we can take this structure, and this is an equivalent representation in which you take these different inputs and relate them to each other. For example, when the driver does something, the inside context changes, and driver may be moving things in time, so you can encode that intuition. In second example, this is the human modeling motion part. Here, you have certain nodes which you are trying to track, and in this case, we want to track a spine, arm, and leg. There must have been a head, but I think it's combined with the spine in this particular experiment. And there are these different types of temporal behaviors that usually change, and the relations between the two. And this helps you model how the human is moving over time. And each of those RNNs, you can take your favorite one. For example, for edge RNN, you can use this architecture, and for the node RNNs, you can use a different architecture, whatever you felt was working perfectly. And here is a cool thing that one can actually see by doing such kind of compositions. So you are seeing a slow-moving human and a fast-moving human. You can combine the different structures, and you can create a human which is limping, because imagine like a human has some cramp or something. So you can create these different scenario in which now you can actually model a human which is trying to limp across. So it's a really nice intuition. The one thing I liked about this approach is that I can take these learned models and understand what each one of them meant and combine them to create something interpretable. And in the later part of the talk, the last 2 slides, I will also show that it would be extremely hard to share a giant neural network and try to adapt it to different tasks. You have to kind of break it into pieces. And one of the way to break it into pieces was what we saw in the previous talk, which was this progressive neural networks. Another way to break it into small tasks is to come up with these semantic distinctions, so that you can share this activity RNN with some other concept flying around in the world, which is learning the activity RNN. So you can learn from way more data, this part of the model, and this part of the model could learn from some other data, and that makes it very, very powerful. So the second thing we applied was obviously human-object interaction, and we got insane gains about the performance, which is not surprising in hindsight. These are some results. So now what we are doing is we are addressing many such different robotic tasks. And I will dwell on this image a little bit, but one thing you can imagine is, let's take the example of this Robobarista project, where the robot is trying to move its joints by reading this manual, which is a natural language, and looking at the real world in the same time. The cool thing that happens here now is that you can take the looking part of this model, share it with this bottom thing, because, well, this data set and these models were also doing the same thing. They were looking at human environments. And in fact, you can just, for example, take thousands of YouTube videos and learn from that also, because the visual part of the model is actually shared with so much visual data that we have created over the past decade, thanks to many of the video sharing websites. This part of the model, which is dealing with the language, you can share it with another project called the Robot Language or Tell Me Dave project. And a parallel project is also going on in Stephanie Telex's lab at Brown, where they have been learning different kind of natural language representations. So imagine using that relevant language model, using some relevant model, and by reading all the recipes on WikiHow on the internet, you can train that part of the world and give it to the robot. And lastly, the robot in this case is only dealing with kinematic interaction, because contact is not so important in doing appliances. There is only one last point of contact when you're pressing a button or turning a handle. But it can learn from manipulating food item, where contact manipulation is extremely important. So it can actually connect to deep MPC type of models where contact manipulation becomes important. So this is the direction we are going towards, where instead of each robot learning in silos, we can create these machine learning models that can have models that can be shared across. So this is the vision I have, and so far we have been making small steps towards it. So far we described how you can design systems that can learn from visual data, from robot kinematics, and apply it to different problems, like figuring out how the car should behave or the robot should behave. We have yet another source of information, which is basically we have parsed thousands of YouTube videos. So I'm very surprised that there are like 10,000 videos of how to make an omelet and 20,000 videos of how to make a pancake. And we don't even need to collect data anymore by robots. Why buy $10,000 robot arms and make them do this all the time? Well, watch tens of thousands of videos, learn the visual part from that, identify, as long as you're very clear that this is the part that you are borrowing from the internet videos, give it away to the robot who is doing something in the real world, and that is how the learning can become very, very fast. So we did our first demonstration earlier this year when we had a bunch of this. This is the Robobrain. It was running in the cloud. And in this particular demonstration, it used most of the items from this project, where in one project, we were telling the robot to do things when you verbally give it a command, which is, robot, make me an affogato, or robot, make me some ice cream. Ice cream was not correct because the robot cannot manipulate ice cream, but some other simpler tasks. Now, that knowledge was uploaded in this system. There are other projects in the lab going on in which people are playing online games. They are parsing videos. They are doing a bunch of things. But this knowledge, which was done with PR2, was downloaded by Stephanie Relex's lab in Brown by a Baxter robot. And the fun thing was that because the representation was nice enough, it was possible to demonstrate that the robot can do that particular skill. Now, this demonstration was done at a much smaller scale. We have to do much more. But I'm very, very interested in this learning approaches, which not only require lesser work in designing features. So, but also whatever we learn is interpretable and shareable across the labs so that the robots can learn faster. Thank you.
Thank you, Ashutosh. I think we have time for 1 or 2 questions before we head to the coffee break. Any question? Yep.
So it's a great talk. So it would be great if all these different labs could be using all these the same parameters, for example. But that also requires that they're working on similar styles of tasks or with similar robots. So do you have anything in mind in terms of getting people on board with that?
So the question is that it is a great vision to have the research labs share the learned models with each other. But the problem is that the different robots are very different. So I don't see that as a problem because it is correct that the Baxter kinematics and dynamics would be very different from PR2. But if you encode the level of representation, which is the following, that if you are interacting with a cup in this particular image on the top bottom left over here, and there is another cup here, and there is a tub here, and there is another tub here, at that manipulation level where what is the end effector's position with respect to the object, that is the part that could be shared. So I think the trick here is in not throwing a blind learning algorithm into the system where pixels go in and labels come out, but try to learn models which are encoding or making a parallel to the physical reality, which is that object is a physical reality, and even if you change, things move around. And then the contact between the end effector and this is a physical reality. Kinematics is a third physical reality. So if you divide and conquer, I believe this sharing could become possible.
Any more questions? All right, so then I think we go for the coffee break. We'll be back here in half an hour for the poster presentations. And after that, we'll hand over the best paper award, and then we'll have the panel discussion with all of the invited speakers. So see you all back here.